welcome to the lectures on evolution of air interface towards 5G. So, we are discussing propagation model. In the previous lecture, we have discussed the large scale propagation model, where we have primarily seen the path loss as well as the shadow fading parameter, and we have also given you expressions or some samples of the path loss including shadowing expressions, which are typically used for evaluation. So, briefly we have discussed about the average received signal strength in the area, which is predicted as a function of separation distance between transmitter and receiver d, which is predicted only by path loss, is enhanced with a shadow fading parameter S. In the dB scale, we have declared that it is Gaussian distributed and with a 0 mean and a standard deviation sigma sub chi or x dB. It is given in dB, because this entire equation is in dB. So, that is also given in dB. And then we have expanded this thing, and we have said that one can look at the typical profiles that are mentioned as example in this particular one, which is about IMT advanced, where it talks about the path loss exponent and as well as sigma parameters. So, that is what we have identified in the previous lecture. So, using these models, one can find coverage probability, which we will shortly see, and we have also been talking about this IMT 2020, which is nothing but the 5G. So, there also we have been looking at the different path loss exponent, and they have not changed over significantly for the 4th generation evaluation models to the ones used in the 5th generation model, and those are path loss exponent. These are the sigma dB, that is what we were talking about. So, using these, one can generate various realizations of the channels, and one can find various performance aspects of it. So, that is something which one should be aware, and we will briefly talk about one particular way of calculating the coverage probability. So, let us look at that. So, what we are interested using these models, because these are talking about large scale propagation models about the coverage probability in a particular area. So, again we will talk about the methods that are used. There are various methods, we will just talk about by the first principle. Beyond this, there are several advanced techniques which have been developed, but it is probably difficult to put everything into one platform, but of course, there are relevant papers which one can follow using whatever we are discussing here. So, the received signal strength in the log domain at a distance d from the base station is given by this particular expression, which we have explained so long, and where x dB represents the shadow fading parameter. It is a random variable with Gaussian probability function, because it is in dB, and with a mean of PRD. So, this received signal power in log domain has a mean value of this, which is nothing but this part, okay, and a standard deviation of sigma, which is for this particular thing, okay. And therefore, it is represented as, that means this is distributed, you will find that this is distributed as normal in the dB, because everything is in dB, with a mean and the corresponding sigma. That is how that is represented. All right. So, the probability, now since this is a random variable, so this is a random variable. So, the probability, that is the received signal strength, that is how we would call it, crosses a particular sensitivity level gamma, right. So, this is in dBm, right. So, this is received signal strength is in dBm, crosses a certain sensitivity level, which can also be given in dBm, is given by the probability that the received signal strength is above that threshold. That is it, that is what we want to calculate. So, that is simply integrate from gamma to infinity the PDF probability density function with the variable s. Yeah, that is where we are back. Okay. So, this can be expanded as 1 minus integrate minus infinity to gamma, and you can clearly recognize this is the CDF. So, which is 1 minus, it is less than the threshold gamma, which can be expressed as 1 minus the CDF, and since it is Gaussian distributed, we now know what it is going to be, half complementary error function gamma minus the mean value divided by root 2 sigma. So, we see that we can calculate the probability of coverage at a particular distance given the description of the path loss model, and as one increases the difference, one can find the coverage probability at that particular distance. So, this of course can be translated to Q function, where you can see that half and root 2 has been absorbed. That is the standard translation. So, what we are interested in calculating is the circular coverage area, which is determined by the radius r sub gamma. That is, r sub gamma is the radius at which the signal level crosses the threshold gamma, right, and what is the probability of doing that. So, you define a coverage area as a coverage area is maybe a circular coverage area with a particular radius, wherein at the boundary the signal crosses the threshold of gamma with a probability that probability that received signal strength is greater than gamma, which is defined as prob r gamma, right. That is it, that is the probability value. So, that is how you define the coverage probability, that at the boundary with this radius what percentage of time one is covered. So, which is the likelihood of coverage at the cell boundary. Let me clear off all the ink on this particular page. Yeah. So, the likelihood of coverage at the cell boundary with D will now be set equal to r gamma, that means coverage at the cell edge. So, the way to do it is whatever probability of coverage we have been discussing can be associated with an infinitesimal small area at a particular distance d from the center, and then we can simply integrate or average out this probability over the whole area. That is the whole idea, that is what we want to do in order to find the coverage probability. All right. So, moving ahead now. So, the percentage useful area is simply the area averaged probability of coverage, right, that one can calculate, and to do that it is sometimes essential to translate the expressions in terms of received signal strength at the cell boundary or the cell edge. Then things becomes easier, because through path loss model one can easily calculate the average received signal strength at the cell edge, and from that one can do all the calculations. So, things are better. So, we know that the average received signal strength at a distance d is by this expression. We have been talking about this, and now you have to translate this expression to the one in terms of r gamma. So, if you look at the expression between this and this, there is no such big change, because this d is now replaced by r gamma and it is again cancelled by r gamma. So, the equation remains the same, only thing is that we have introduced the parameter r gamma. The advantage is when we look at the entire expression, that means if we look at this particular block, then one will easily recognize this is P r at r gamma bar, that means the average received signal strength at cell edge. So, we can now reference things with respect to this, and P r d 0 bar is nothing but the average received signal strength at d 0. We have defined what is d 0. In the next few steps you replace d with r, because that is the cell radius or the radial distance, and therefore, you can use the probability of coverage at a distance r from the center is the same expression, where the d is replaced by r, and the same expression it was complementary error function which you have expanded in terms of error function, and then this P gamma, that is what you have over here, P average received signal strength, you have expanded over here, which is again not new, and then what you can find is again this at the denominator and at the numerator cancels out. So, it is the whole expression is nothing but the received signal strength at that distance, right. All right. So, we will erase some of the ink to reduce the clutter. Okay. Proceeding further, what we now do is we club these two terms over here and the rest of the terms in the next term, and we have a meaning associated with it. So, we say that let A denote this thing. So, this is A, and we also have this thing denoted as B, right, that is what is given below. So, if you have these two replacements, you can have probability of coverage in terms of error function as written in the expression above. So, now one can use the different path loss models that have been described in order to calculate the coverage probability at the cell edge. Once you calculate coverage probability at any distance or at the cell edge, then you can go back in calculating the percentage useful area of the cell. That is possible. Now, one quick interpretation on this is that if you concentrate on the term A, what we have, I mean, if we look at this, A multiplied by root 2 multiplied by sigma x dB is equal to gamma minus P r or gamma bar, indicating that this term is capturing the difference between the sensitivity level and the received signal strength, right. So, let us say sensitivity level is minus 75 dBm and the received signal strength is minus 70 dBm. So, this term is able to capture the margin that is present between the sensitivity level and the average received signal strength, and that influences the coverage probability. So, you can now see in terms of margin, and that is because you have over here the average received signal strength at the cell edge, and that is why the earlier introduced concept of translating things to cell radius and received signals power at cell edge is very, very important. Right. Moving ahead, then as we said, one can calculate FU, and there are different ways of doing it. You get certain expressions. Well, this is available for reference, but that is it. Okay. So, we have discussed about the margin, and that is a graphical representation of what we have just discussed. So, there is a threshold, and this is basically P r received it is P r of r gamma bar. So, that is, and this particular thing is the margin, right. So, if we are actually calculating, we are actually calculating this particular area, which is kind of outage probability. So, clearly if this is fixed and we want a higher coverage or lower outage probability, then we should shift this entire thing upwards. In order to shift the entire thing upward, all you can do is to increase the margin. If you increase the margin, your average received signal strength will now shift there, okay, and hence your mean point is supposed to shift over there. So, you are going to get your curve which will look like this, right, and hence your area under coverage will be this. So, therefore, which is a much smaller area, and you have reduced the outage probability, or you have increased the coverage probability. Now, to shift this upwards, you can do two possibilities if you look back. So, what you have is a PT term over here. So, basically you have to increase this term. To increase this term, either I can increase this PT term, that is increase the transmit power, or I can decrease this term. So, that means the path loss value would be smaller, and hence this overall expression has to increase, which is nothing but this expression, correct. So, there are two ways to do it, and that is pretty logical. If you reduce the cell coverage, if you reduce the cell radius, then you have increased the coverage probability, or if you increase the transmit power, you have increased the coverage probability, but the problem is interference comes into play and you have to handle it in a different manner. So, there are certain examples assignments which will be made available, which you can take advantage of and work on using these things. So, with this we move on to the next set of discussions, especially on the channel structures, which is primarily about the small scale fluctuations. So, that is very, very critical. So, we have talked about the large scale fluctuations, and so we are done with the large scale fluctuations. We will take an overview of small scale fluctuations, so that we understand what happens, so that we can quickly look into the effects of MIMO, or how does MIMO work and what is the advantage, and you can probably devise better schemes even beyond what exists today. So, in the small scale fading, we have actually described the small scale fading. So, we will briefly take a look at some of the fundamental models. So, here what we assume that you are taking a top view of this plane. So, basically you are looking from top, and there is this floor area, or there is a road on which vehicles are moving. So, you are seeing basically from top. Okay, that is what is happening. So, the vehicle is moving along the positive x axis with a velocity v, and there is a incoming plane wave from a particular direction, indicating that your mobility is in this side and some base station is here and the signal is coming there, or it might come via reflection also from that particular direction. Okay. So, E field is along the z axis, that means it is kind of in this direction, and theta n is the angle at the ms. So, certain assumptions are that transmitter receiver separation distance is very, very large, and one can use 2D model for wave propagation. So, that is what we have already discussed. So, it is the same issue now that what we are talking about. So, the Doppler due to mobility is given as f d n is equal to f m cos theta n, where you have f m denoted as V c V by c times f c, which is the maximum Doppler shift. So, you can clearly see that if cos theta equals to 0, that means if it is coming from this direction, then the Doppler shift is maximum. If theta is from the opposite direction, that means if it is in the reverse direction, it is negative of that value. So, the least possible value in that case, or the negative of the amplitude or the maximum value, and any other direction you can replace with the cos theta. This is a component of Doppler along the direction of mobility, okay. And the rest of the terms are defined over here. So, the transmitted band pass signal one would usually write as the real part of the baseband complex envelope S tilde t e to the power of j 2 pi f c t. That is a standard model, and S tilde t is the complex envelope of the signal. There are n propagation paths, and therefore, the received signal R t. So, that means, if we recall the diagram, there is this base station, there is this user device, the signal comes via multiple paths forming different angles, and each of these angles are theta n. So, the received signal is a summation of the signals that has come via the different paths, with coefficient C n indicating the attenuation or amplitude factor of the signal coming along the nth path, and each of the path has an associated Doppler frequency with it. So, f c plus f d n, and what we will see is that the signal that is received at time instant t, is the original source symbol, but it must have started at a time tau units before the present time. If it starts at time tau n units before, that means it has taken a propagation time of tau n corresponding to the delay associated with that particular path, and hence we have t minus tau n replacing t in all the equations. So, we proceed with this. So, that is basically the signal structure. So, this is the received signal which we had seen in the previous page, and if we expand the equation, what we will do is we will just see e to the power of j 2 pi f c t is the term which we have collected over here, and rest of the terms we have kept together, and there is a specific reason for this, because e to the power of j 2 pi f c t is the situation what we would like to handle separately, because this is the passband signal, and with the real part of it. So, what we can clearly realize is that this is the equivalent received baseband signal when this has been transmitted, and that is what exactly is written over here. So, this entire thing is equal to R tilde t, right. So, that is what has been expected, and then in the next expression what we have is this entire term is we are collecting together into the term phi n of t, indicating that each path C n, each nth path is having an associated amplitude and an associated phase with it. This is very, very important, and the signals via each path are coming with a delay. That means, different signals are coming via different paths, right. So, the signals which have been generated at different instants of time corresponding to the path delays are coming and getting added together at the receiver. So, this is causing ISI, and this is well known. So, what we look at is the phase component associated with each of the paths, and one can easily calculate the phase difference because of path difference and so if you are taking the delta at the same instant of time, that means if two paths differ by delta tau n, two different paths, then we can compute the resultant difference in phase. So, simply since let us take f c is almost equal to 1 gigahertz, let us neglect f d with respect to 1 gigahertz. So, what we have essentially is the path difference between, let us say 2 is 2 pi times f c times delta tau n. Now, if you let delta tau n is approximately equal to 1 nanosecond, which means that two path lengths are different from each other by 1 nanosecond, what you will find is that the phase difference is 2 pi times 10 to the power of 9, 1 gigahertz multiplied by 10 to the power of minus 9, that is 1 nanosecond. So, together it is giving you up around 2 pi phase rotation. So, if two paths are different by 1 nanosecond. So, if you take the speed of light, it will approximately turn out to be 0.3 meters, that means 30 centimeters. If two paths are different by 30 centimeters, there will be a 2 pi phase difference, and then you are adding up several of them. So, even if paths are different, even less than 30 centimeter different. So, you are going to get the phases which are spanning 0 to 2 pi, and many of them are coming together and you are adding them together. So, what you can see is that there is a mixture of different phases along with different amplitude factors associated with the coefficients of reflection. So, this particular channel representation of the received signal that we see over here can be modeled as a linear time variant filter having a complex low pass impulse response given by g t t comma tau as given in this particular expression. So, if you compare these two, you will easily figure out that these are coefficients of the channel impulse response, where the channel impulse response is given by this particular expression. So, where each tap has a gain factor and a corresponding phase factor. So, then we are interested to look at the channel impulse response characteristics at any instant of time. So, what we will find is, we have actually discussed that part. So, what we will now make is a very important assumption, is that let the delays, the relative delays be very small relative to the symbol duration. So, that means if we assume that the symbol duration is really large, that means T s is the duration is much greater than delta tau n, I mean for all n, let us say, right. That means, I mean this is not the exact notation, because we are talking about difference between two delays. Then we can approximate all the different delays to one particular delay, that is tau cap. That is a kind of situation. So, what is that? So, this is the situation when all the path lengths are almost same, right. So, if they are on an ellipse, if all the scatterers, reflectors are on an ellipse whose two focal points are the transmitter and receiver. So, in that case the length would be the same, and that is a kind of approximation or a scenario that we are looking at. So, under that condition we will find that the impulse response which we had drawn, okay, which we had written, can be written in this form. That means, you are going to get delta tau minus tau cap instead of tau n. So, you are removing this tau n, and hence this is out of the summation, it goes beyond the summation. So, this entire set can be written as g t with the single delay factor, right. So, that is what is the channel impulse response, and you are interested in the Fourier transform of it. So, if you take the Fourier transform of the channel impulse response, so you get it as capital T f, and you just look at it, there is a delta function, you take a Fourier transform, it is g t with e to the power of j 2 pi f tau cap, right. And then what we are interested in is the amplitude response. So, if you take the amplitude of g t, what you will find is that the modulus of g t, modulus of T f would be left with a modulus of g t. So, that means it is not a function of frequency anymore, and this is primarily because of this assumption set that we have made. So, under these conditions the amplitude response is not dependent on the frequency. That means, if we have a frequency f, and if we write t of t comma f at a particular instant, it will be a constant value across all frequencies, and if we have time in this axis, then at every instant of time we can imagine that this bar to be at different values, right. That is what this bar is going to fluctuate like. Okay. So, that is what gives rise to flat fading, what we have been talking about for a long time, and that is one of the components of the study. That is what we have been looking at, right. Okay. Quickly we can even say that if that condition is not true anymore, that means if this condition is not true, 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 that means we are left with a situation like this. Then what is going to happen? That means we do not have a situation where the transmitter and receiver are at the focal points of an ellipse and all reflectors and scatterers are coming from the same ellipse. This is not the right path, I mean it is like this. What if there is, they are the focal points of other ellipse also, and the signals keep coming like this. So, that means there are resolvable delays, right. So, let us take a quick look at what happens when they are resolvable delays. Right. So, that is the kind of picture that we get when there are resolvable delays, and there are groups of reflected waves which come at a certain delay, which we have just finished studying. Another group would come at another delay, and we have also studied the effects of that. Another group would come at another delay, which we have also studied. So, what is happening is, if you would launch an impulse, an echo is going to come at a certain delay, which is let us say tau 1, and here all rays from different directions are going to come, and they are within the same delay unit, that is tau 1. The next group of echoes are going to come together and they will add up and will not be able to recognize them separately. So, this one would be g of t comma tau 1, this would be g of t comma tau 2 in correspondence to what we have just discussed. So, in this situation what we have is all the properties that we have discussed in the previous set, same and valid for any one particular delay at any particular delay, but we have this entire series that is valid in the entire thing, and each of them fluctuate in time according to their own policies. Policies in the sense in a random manner. There are various ways of structuring this, there are various models of doing it. One of the most common models that are used is wide sense stationarity uncorrelated scattering model, which is followed in such analysis. So, we will just briefly tell you the effect of such a thing. So, what we have is this expression, which you can easily recognize from the previous set of equations that we had been talking about. We had made the assumption that let these different tau n's be replaced by tau cap. Now, we are saying that no, let us go back and keep this original tau n and see what happens. So, simply you are going to expand this this expression. So, you can decide to omit this because it is just rewritten over here. We have the same expression over here. So, you simply have these things as delays and these coefficients. So, we have already explained that at each delay you are going to get adding up of all the different rays that come at the same delay. So, any one of them, if I look at this, would correspond to g of t comma tau 1, this thing would correspond to g of t comma tau 2, and so on and so forth. So, basically this is g of t comma tau 1 multiplied by delta tau minus tau 1 multiplied by delta tau minus tau 2, and so on and so forth. Now, if you take the Fourier transform Fourier transform of this, it is a linear operator plus Fourier transform of this plus Fourier transform of the next, and so on and so forth. Each one of them are flat, that is for sure, but they come with a certain phase factor. It comes with a certain phase factor, right, and so when they add up together, they create a complete different picture. So, what we will see is that if you look at the graphical representation, if there is only one tap, only one equivalent delay, this is the frequency response that you are going to get. If you have, let us say, 2 delays, then the frequency response time snapshot, that means at any instant of time at t equals to, let us say, t1, it is not tau, it is time, it will be this. As the number of delays, resolvable delays increase, that means in this case if I say I have tau 1, tau 2, tau 3 and so on, the channel becomes more and more frequency selective. Why do we call it frequency selective? The simple reason is, if I look at this last one, or maybe if we go further, this particular one may have tau 1, tau 2, tau 3 and so on up to some tau n. These set of frequencies, we just change the color to match it, are allowed to pass through with a certain amount of gain. If we look at another set of frequencies here, these set of frequencies are kind of relatively attenuated with respect to other frequencies. So, again we choose back the color. These set of frequencies are allowed to pass through with less attenuation, and these set of frequencies are kind of subdued or they are more attenuated. So, there is selectivity across the frequency compared to flatness across the frequency between the two conditions. So, this is again a very vital situation that we have to use while studying the different effects. So, we stop this particular lecture over here, and we will continue with one more lecture at least to consolidate these issues before we can get into the study of MIMO communications. Thank you.